An 825 Newton window washer is standing on a scaffold supported by a vertical rope at each end. The scaffold weighs 150 newtons and is 3 meters long. What is the force in each rope when the window washer stands 1 meter from one end? Okay, just like our other problems, first thing we're going to do, draw ourselves a picture. So, got this window washer standing on some scaffolding. So there's two ropes hanging down, scaffolding in between, nice aluminum scaffolding. The window washer's on here, washing the windows. Okay? So let's draw him in. We know he's 1 meter from one end and it's 3 meters long. He's about a third of the way over. So there's our window washer. Okay, and it's 1 meter to the window washer from one end, and I chose the left end. Okay? What else do we know? Well, we know the window washer is 825 newtons. That's his weight. That's the force of gravity acting on him. So I'm going to say that's the force of the window washer this time, or the force of the person. It's 825 newtons. Okay? Supported by a vertical rope at each end. So each of these vertical ropes is going to have some tension in them. So I'm going to call this the force of tension 1. And this force, tension force 2, okay? The scaffold weighs 150 newtons and is 3 meters long. So from here all the way to the end is 3 meters, okay? And it has a weight of 150 newtons. Now, where do we put that weight? Well, we're going to assume that this scaffolding is uniform, okay? It's the same throughout. So we're going to put it at the center of mass. And since it's uniform, the center of mass is going to be at the center of the object. So right at the center, and that is only 150 newtons. Okay, and it's at the center, so it's 1.5 meters from either end. What is the force in each rope? Okay. Questions asking us for the force in each rope. Now you might be thinking the force in each rope is just going to be the same. You know, figure out the total force and half for each of it. Okay? Unfortunately, that would be incorrect. Okay? If you want to see this demonstrated, go ahead, find yourself a meter stick, okay? And then take a calculator, put the calculator in the middle of the meter stick. You hold one end, have your friend hold the other, and kind of decide how it feels that way. Then move the calculator really close to your end, decide whether it feels like you're holding more or less, then move it towards their end. You're going to find when the calculator is closer to your end, you have to support more of the weight, okay? Same idea here. So tension 1 should be bigger than tension 2. And we're going to figure out exactly how big each one is. All right, so we want to write down our givens in a little bit more of an organized way. So let's look at all these different things we've got. We've got tension 1, so force of tension 1. We don't know what that is, we're trying to find it. We've got the person, so the force of the person, which is 825 newtons. We've got the scaffolding, the force of the scaffolding, which is 150 newtons. And we've got the force in tension 2, and we do not know what that one is. Okay? Now, when we go to solve this, we're going to go ahead and use our rotational information, okay? So this scaffolding is not rotating, all right? If it were rotating, it would be spinning around one way or the other. And it's not rotating, so we have to choose a point of rotation, okay? When there's no given point of rotation and there's more than one unknown force, what you want to do is you want to choose the point of rotation to be at one of the forces. Okay? So if there are two unknown forces, choose to put the fulcrum, pivot point, at one of the forces. Okay? This is important, okay, because we're going to be using torque, and torque is force times distance times the sine of theta. If the distance is 0, we've eliminated it, okay? And so it'll help us to solve our equation. All right, so again, the torque equation is force times distance times the sine of theta. So for each of these forces, we need to put the distance from the pivot point. Okay, so the distance to tension 1 from the pivot point is 0. It's right there. Force 1, tension 1 is being applied right at the pivot, okay, at the fulcrum, so it is 0. The person is 1 meter from this pivot point, so the distance to the person is 1 meter. The center of mass of the scaffolding is the center, so it's 1.5 meters from either end, and so from this end it's 1.5 meters. And the distance to tension 2 is all the way at the other end of the scaffolding, so that is 3 meters. And now we need the angle, okay? Well, it's pointing straight up. Doesn't really matter in this case because the distance is 0. But the angle for the person, I start at the pivot, go down my lever arm, and then go in the direction of the force. That's a 90-degree angle. The angle for the scaffolding, again, start here, go over, go in the direction of the force. It's, again, a 90-degree angle. And then the angle for tension 2, go down the lever arm, go in the direction it's going. That's a 90-degree angle. So we got a lot of 90-degree angles here. Now, this is not rotating. Since it is not rotating, we know that it is in rotational equilibrium, which means the net torque is equal to 0. And again, torque is equal to force times distance times the sine of theta. So I'm going to go ahead and put down all of the torques. Now, I could write down the torque due to tension 1. Okay? However, if I look at this, there is no torque due to tension 1 because it's being applied at the fulcrum. Okay? So that's actually going to be 0. So I don't have to write the whole thing out here. Then I'm going to add to that the torque created by the person. That's the next one I see if I'm just moving left to right. Okay? Now the torque created by the person, if the person's the only thing on this scaffolding and the pivot point is right here, this scaffolding is going to rotate in the clockwise direction. So that is a negative direction, so it is a negative torque. Next up, we want to get the torque created by the scaffolding itself. Okay? And again, we're going to go and look at that force that's here. It's being applied in this direction, which would cause the torque to go in the clockwise direction. So it would rotate clockwise. That's negative, so it's another negative torque. And then I go to the force and tension 2. That force would cause the scaffolding to rotate counterclockwise. That is the positive direction, so it is a positive torque. And all 4 of those add up to 0. Again, the first one was 0, so if we don't include it in our equation, that's fine. Okay, so now we're going to go ahead and substitute some things in. So torque is force times distance times the sine of theta, so I'm going to put negative and then the force for the person, which was 825, times the distance to the person, which is 1, times the sine of 90, plus the force for the scaffolding, negative 150, again negative because it causes the object to rotate in the clockwise direction, times the distance to the center of mass, which was 1.5 meters, times the sine of 90, plus the force and tension 2, which we do not know, the force of tension 2, times the distance to that force, which is 3 meters, times the sine of 90. All that adds up to 0. So let's simplify each of the terms here. So we get negative 825 plus negative 225 plus 3 times the force and tension 2 is equal to 0. Combine our like terms, we get negative 1,050 plus 3 times the force of tension 2 is equal to 0. Add 1050 to both sides and divide by 3. Oops. And we will get that the force in tension 2 is equal to 350 newtons. Okay, we've got 1. Okay, this force is 350 newtons. We were supposed to find both. So what are we going to do? Well, this was not rotating. That meant it was in rotational equilibrium. It's not rotating, but it's also not accelerating up or down, which means that it's also in linear equilibrium or translational equilibrium, which means the net force in the y direction, since it's not accelerating up or down, is equal to 0. Then we simply add up all the forces in the y direction. Well, I start on the left. First one I see is the force of tension 1, and that is going up, so it's positive, plus the force of the person, that's going down, so negative, plus the force of the scaffolding, which again is pointing down, so negative, plus the force of tension 2, and that is pointing up, so positive. All 4 of those add up to 0. Force and tension 1 we do not know. The force of the person is 825 newtons, so negative 825, plus negative 150 for the force of the scaffolding, plus positive 350 for the force of tension 2. We add all these like terms together, move them to the other side, we find that the force of tension 1 is equal to 625 newtons. And you can see that the left one, this one, was more because the person's closer to that side.